So we will start with the electric field lines. Electric field lines.
Okay.
So far we have studied about electric field, its definition, and the electric field due to point charge.
Yeah.
Right? So earlier I told you that electric field lines, they are imaginary lines. Okay,
Yeah.
imaginary lines.
Are you sharing the screen?
Oh, just wait. I think I forgot. Can you see it? Is it visible?
Yeah. Yeah.
Okay. So I told you I know that electric field lines are imaginary lines of force,
Yeah.
just like we have magnetic lines of force, right? So today we will
Yeah.
discuss the properties of electric field lines.
Okay.
Correct. So first we will define what is this electric field lines. So it may be a curve like this, okay,
Yeah.
and it should have an arrow to indicate the direction, or can be like straight line also. Okay,
Okay.
it depends where these are coming from, right? And I also told you that if you want to find the direction of force at any point on this line, you place a positive charge plus q naught here,
Yeah.
right? And the tangent to this line will be the direction of force on this charge q naught. Okay, because positive charge are drawn in the direction of electric field, right?
Yeah.
Similarly here, if you see, you place this charge here q naught, so the q naught will experience a force in the direction of electric field in this way.
Yeah.
So that's how the definition also goes. So electric field lines, what are they? They are the curves, okay, along which a small positive charge would move when free to do so in the electric field.
Yeah.
So what it means that if you freely if you put a charge here and you free it, like it can move anywhere, so it will move in this direction, in the direction of electric field, because at every point it will experience a force in this direction, right?
Yeah.
So it will trace the path. This q naught, if it placed here, it will trace this path, the path of the electric field, isn't it?
Yeah.
So that's what it is written in the definition. And furthermore, the tangent at any point on electric field lines gives the direction of force, right?
Yeah.
At that point. So this is the definition. You can write it.
Okay.
So in fact, I told you in prior that they are imaginary lines, so they don't exist physically, right?
Yeah.
But their existence is important, so that's why we draw them to solve various problems.
Okay.
Okay, so now we'll write the properties. What are the properties of electric field lines? Let me change this to some other color. Hmm, so properties of electric field lines. You can see in the book as well.
Which page?
Oh, it's on 1.46.
Oh,
Okay, can you see?
yeah.
So the first property is that these field lines, they are continuous smooth lines. What does it mean? It means that they do not break in between. Okay,
Yeah.
so without any breaks, correct?
Yeah.
So there cannot be an electric field like this because it is breaking here, right? This is wrong. Now let us write the second property. You can remember these all as well because they are important.
Okay.
So the second property is that they start at positive charge, because I told you if there is a positive charge, so it will emanate electric field, right?
Yeah.
So in any case, what's happening behind the scene? I can hear
You
loud
know.
noise.
What can you hear?
Loud noises.
Like banging?
Yeah,
Oh yeah, it's because I'm in the kitchen. I cannot hear that though because I have earphones on.
I am getting it quite loud.
Um, is it still loud?
Yeah.
Oh, okay, 1 minute.
So this is the second property, that they always start at positive charge. There is no way an electric field can end here like this because they always emanate from the positive charge, right?
Okay.
And what happens? They end at negative, okay? So they start at positive and they end at negative charge. So if you draw a negative charge, and the electric field will look like this, okay? For a negative charge, I told you we will discuss it later, so that's the point. Okay, so positive charge will emanate, and the negative charge, the electric field line will converge here at this point at the charge. Okay, so we can say that the electric field lines, what they do, they cannot form closed loops. This is important. For example, If someone says to you that is this an electric field? Is not an electric field because they cannot form closed loop. Then the initial point is they should start at positive and they end at negative. So this cannot happen. This thing is wrong, right? They cannot form the closed loop. And if there is a single charge, what will happen then? So like this, okay? Here there is only a single charge, not the like two charges or combination of two charges, okay? So if there is single charge, then what will happen? In case of positive charge, what will happen? The electric field lines would start or end at infinity. For example, in this case, they are going away and they would approach infinity.
Yeah.
So in the case of positive charge, they will end at infinity, and in case of negative charge, they will start at infinity. So it must be coming somewhere from far distance, infinity. Okay,
Yeah.
that's why we written electric field lines would either start or end at infinity when there is a single charge. We'll discuss about the combination of charges as well. So in a moment, we'll discuss that because you need to remember these properties. The third property is the tangent at any point on electric field. Okay, what it gives? It gives the direction of electric field at that point, or force. Gives the direction of electric field, or you can say the force. Correct?
Yeah.
Fourth one is what? No two lines of force can cross each other. This is also very important. So no two line of force can cross each other. Why so? Let's say someone gives you like this. This is an electric field, right? E1, and this is another electric field. Is this a valid electric field? Consider this point. This point. So at this point, the direction of electric field would be the tangent direction.
Yeah.
At this point, it will always be like this. But what happens at this point? At this point, you are getting the intersection, right? They are crossing. So what will you say? The direction is also in this way and direction is also in this way. So if you put a positive charge Q naught here,
Yeah.
I'm again hearing banging noises.
I don't know what to do because I cannot move around.
Is not there any empty room?
No, there is no empty room. If I go to my mother's room, she would be there.
What? No, it is quiet. It is quiet now. Yeah, it is quiet. So I was talking about the force direction at this point, the intersection point. So what will you say about the direction of force when there is a charge Q naught placed at this point? So there will be two direction of forces. So how can you decide which one is correct? Now this is ambiguity. Because like it is not confirmed where the direction of force would be.
Okay.
Can a charge move in two different directions at the same time?
No.
So how can this be correct? Like we said that at any point on the electric field, the tangent
Yeah.
gives the direction of the force. If you place a charge here,
Yeah.
but here you are getting two directions because that the electric there were two electric fields that got intersected at this point, and according to nomenclature we are getting one direction in this way because of this electric field, another
Yeah.
direction of force in this way because of this electric field. That this cannot happen.
Yeah.
Okay, because there is only one direction in which this charge can move. How can it move in two directions at the same time?
Yeah.
It can either move in this way or either in this way. So that's why this whole picture itself is incorrect. That means
Okay.
that the electric field lines cannot cross each other
Cross.
like this, only because of this thing that happened, right? So if two electric field lines cross each other, we cannot find the direction correctly. We cannot find the direction as to in which way it would move. This itself is wrong. That's why we say that they cannot cross each other.
Cross. Okay.
Force is, so it says that the line of force are always normal to the surface of the conductor. You write this at this point and we'll discuss it later when we move on to the conductors.
Okay.
So there is a altogether different topic. So line of force, which is also this is also called electric field lines. Same thing, right? Electric field lines are always normal to the surface of conductor. Conductor can be anything. For example, this is metallic ball, right? So we'll explain it later in the, I mean, meantime we'll move on. So actually this is a conductor. So what we saying that electric field lines are always normal to this, like this. This is called normal. What is normal? See, this is the tangent, and the 90-degree line to the tangent is called the normal. Okay,
Oh.
so this is the tangent at this point, and this line, this is the normal. So the electric field lines to a conductor cannot be like this angle, at some angle 30-degree or something. This is wrong. Yeah, they will always be at some angle that is normal. Let us draw the wrong one with some different pens. So if it is like this, theta, this must be wrong, right? This is correct. Have you lowered your volume? Yeah, I think they are lowered.
Lowered my volume.
Yeah,
What? Oh.
I cannot listen to you properly.
Oh, like this.
Yeah,
Hello.
yeah.
Not a nice.
The sixth one is that the lines of force, they
Tendency to contract.
they
Like what?
contract lengthwise. Okay, we'll discuss this in a moment. Just wait. And the seventh is what they do is they expand laterally. This is also, we'll just see. So contract lengthwise means it explains the scenario of attraction between two unlike charges. We know that two charges attract each other which are
Yeah.
opposite. Attraction of unlike charges can be explained by this this thing, that the electric field lines, they contract lengthwise and they
Yeah.
expand laterally. This will explain that repulsion, the repulsion of like charges. We'll just see, just wait. Okay. And eighth one is, this is also important, so the relative
Closeness of the lines.
closeness gives, or you can say it gives an idea, gives an idea of strength of this, of the electric fields. Okay, the strength means the magnitude, that the 10 newton per meter or 20 newton per meter. Like he's saying this thing, for example, this thing. So here you can say that at the point ABC, let's say this is ABC, this is EFG. So here the distance between the 2 points is less, this distance. And here the distance between the 2 points on the electric field is large, right? So the closeness, the more the close they are, so the larger will be the magnitude of electric field. Here the magnitude of electric field will be lower because they are far apart and they are close apart here. Correct? And furthermore, he's saying that the lines of force are close together in a strong field. So it's the same thing. It implies the strong field here, okay? Where the field here is strong because they are close to each other. And far apart in weak field, same thing. Here they are, the weak field is weak. And parallel and equally spaced in uniform field. So if there is the uniform field, the electric field lines would be parallel and equally spaced, like this. What does that mean?
What? Parallel.
Yeah, this is parallel and equally
So
spaced.
that would mean that the
Uniform electric field. Okay. Let's say here the electric field is 10 Newton per meter. Okay. And here it is 5 Newton per meter. It is differing because the electric field lines are neither parallel nor they have equal distance between them. But in case of uniform electric field, the electric field at every point would be the same. For example, if it is 7 Newton per meter here, it would be 7 Newton per meter here. Everywhere it would be 7 Newton per meter. That is called a uniform electric. Okay? And again the direction will be in this direction at any point. Okay, this is what a uniform electric field means. And the ninth one is that electric field lines, they do not pass through a conductor. So if there is a conductor, or let's say there is this electric field lying in the space, right? And if you place in a conductor in this space like this is a, like, let's say this is a box of metal, and electric field lines would not pass through it, would not pass. Okay, this is called, we'll discuss why it happens. We'll discuss why it happens that the electric field lines do not pass through a conductor, but again it's a topic on conductors. Okay, it will come later in the course, due course. Now we will sketch the electric field lines due to different type of charges. Okay, so for the positive charge we already know what will be the case. So sketch of electric field lines for the positive charge. Yeah, very easy, right? Like this.
At negative angle, right?
Yeah, so it is spherically symmetric, we already studied, like, right? This we call as spherically symmetric. So you can write it, it is radially outwards. Again you can write it if you want, because so this is radially outwards and this is spherically symmetric. Okay, and they extend up to what? They goes on up to infinity, correct? Similar is the case of negative charge, except that the direction would be the opposite direction. So they come from infinity and end at this charge. Okay. So this is the case for negative charge. The symmetricity is same. They are radially inwards. But symmetrically, spherically symmetric again. Okay. Now let's draw for two equal and opposite charges. Okay, so two equal, and so there are four cases. This is the first case for a positive charge,
Okay.
the second case is for the negative charge, the third case is for two equal and opposite charges. So let us first draw two equal and opposite charges placed close together in space. Let's say there are two charges, one of them is positive, another is negative, right? So as we know, the electric field line start from positive and end to the negative, so they end at negative. So like this you can draw the electric field.
Oh, it would be like a magnetic.
Again your voice is not clear, it is very
It
low.
would be like a magnetic field.
Yeah, quite similar to that. Okay, so from positive to negative, right? From positive to negative, from positive to negative. They start at positive and end at negative. Remember, they are not forming loop. This is not a loop, this is a single line. It starts from positive and it ends at negative, that's it. There is no loop here. Okay, because the electric field lines do not form loops, and it goes like this. because we are not drawing all of them, right? So this is the electric field lines due to two positive, no, due to two unlike charges. One of them is positive, another is negative, right? So this type of field is called cylindrically symmetric. This is the dipole axis. So this is also called dipole. Dipole is the arrangement of two charges that are placed at some small distance apart and they are opposite.
Okay,
I cannot hear you.
I said want the negative electric line arrow be.
Your voice is too low.
Is it fine
Yeah, now I can listen.
So I said on the electric line of arrow words.
This one at this point would be
No,
like
not
this.
the one which is like at the outer.
Oh, sorry. I drawn it in the wrong direction, right?
Yeah.
So this should be like this. Corrected me. Thank you. This should be inward, okay?
Yeah.
Now it is correct. Anyway, so I was telling that the dipole is the combination of two charges which are unlike and they are placed close distance at some close distance. Okay, so this is also called a dipole. And this axis is called the dipole axis. The line at the center and perpendicular to this. So we say that this field is cylindrically symmetric. Okay, this is cylindrically symmetric about dipole axis. This is the dipole axis and this is the field around the dipole axis from here to here. So this is called cylindrically symmetric. We will discuss what is cylindrically symmetric in the chapter continue. And now let us take another case. And now one thing, so I left a point here. We were discussing the properties of electric field lines, so I left a point that the electric field lines, they contract lengthwise. Okay,
Yeah.
so here you can see when this is the length, so this is the length.
Type.
Okay, you can say that as they are going close to the charge they are close apart, and when they are not close at this point they are far apart,
Yeah.
isn't it? So that's why I said that the electric field line contract lengthwise. As we move along the length they start to contract, they start to come close to each other.
Yeah.
Okay, so this is the that point. So it explains the attraction of two unlike charges. Where is that gone? This point. So they contract lengthwise. This is explains the attraction of two unlike charges. And the fourth and the final one is we have two opposite charges, so two charges, but this time they are like charges. And we want to draw the electric field lines due to the combination. Okay, let's take a positive charge and another positive charge. Now here both of them are positive, so we cannot draw electric field lines starting from one and ending to another. So at any in any case they would be going from the positive charge,
Yeah.
going away like this. And since these both are positive, because they are not coming close to each other, because they will repel, right? So they are exerting force, so they will not come close ever. They will going like this, going away from each other. And this will go in this direction. Further you can draw more. Isn't it? So they are not coming close. They are at every point, you can see that they are trying to go away from each other, isn't it? Because they are like charges.
Yeah.
So that is the thing that he said in the next point, that
So they
the electric field lines, they expand laterally.
yeah.
So this is the lateral. So expanding, they are expanding like this. They are going away from each other. Okay, this is called that they are expanding laterally. Right? Just a second, hold on. Where is that? Okay, so this is completed. Okay, the properties of electric field lines. Right? So you can write it. Or you want to write it? You wrote it? Okay.
What's the same thing?
Again, your voice is low.
I said it in the textbook also.
Yeah, it's there. You can learn or write from that also. See, the textbook may contain topics that are no excluded from the syllabus as well. So either you mark them, what I am telling you, or you write in the copy.
No, it's I wrote. No, also in the book, like stars and asteroids or oceans that are.
No, this must be like way older. The book might be older, so it may happen that the more syllabus is related, which is not in the book, mentioned in the book. That's why you either tick mark the topics that I'm teaching you, so to
Yeah.
make sure that on only you have to study that topic, right?
Okay.
So we'll do questions that we left that day. I think we were doing some questions on electric field lines, like electric field due to point charge. So we did a question where there were two charges,
Yeah.
and we would find the electric field midway between the two charges, where there is a charge Q is placed. Remember? So
Yeah.
that
Yeah.
that we did, right? Now we'll do another question, right? So let me copy it, and then we will do. Should I do another question of that type, or you did you get what
Oh,
I
I
said?
got it.
Let us do this question. After this question,
Yeah, can I go to the restroom?
right now, you can go right now.
Oh, but we can do this question now.
Okay. So this is the question. So the question is 2-point charges Q1 and Q2 are placed 0.1 meter apart. Calculate the electric field at point A, B, and C as shown. Let me also copy the diagram then, because it is asking. This is the diagram, right? Here it goes. So 2-point charges Q1, Q2. So Q1, Q2 are placed, I think, at this point. Yeah, so one of them is this. Let me change the pen. So one of them is this, and another of them is this. So they are separated by 0.1 meter distance. Since this is the midpoint, so the distance would be halved. So 0.1 divided by 2 is equal to 0.05 meters. So from A to C is 0.05, and from A to, again, this point, let it be some point D, it is 0.05. We need to calculate the electric field at A, B, and C. Where is A? This is A. Okay. So we need to find electric field at this point, and at B point. Okay, this is the B point, which is again 0.05 meter away from this charge. Okay, and we need to find the electric field at C point. So how you would do this? Forget about the C point first. Let's consider the point which is A and B, because they are on the line joining the two charges, right?
No.
So that we can easily do. Let us consider the first case, when the charge is, when we want to find the electric field at A, right? How will you find? See, the electric field at A would be due to the charge at C due to the charge at D. And you can see that one of them is positive charge, another of them is the negative charge. So if I mark it by pink, so let us say this is the pink one, and this is the red one. Okay, so what do you say about the electric field at A due to B? In which direction? Due to this charge C.
Did you see?
This is not C actually. This is Coulomb. So let us mark it. Can say X. Okay.
Uh, it will be in the direction of
Uh, it would be in the direction. This is positive.
yeah,
So it would be in this direction.
yeah, in the direction.
Again, I cannot
Yeah,
hear.
that's right. I said like it will be like towards the right. Towards
Yeah, and due to this charge at D, what will be the direction?
Uh,
If it were positive, then it would repel A. This would, then the direction would be this, right?
oh, yeah.
But since this is negative,
It will be
so it will be the same direction, right? Because a positive charge, if placed here, would be attracted towards this, right? So we can say that the electric field at point A, so you can write like this: electric field at point A due to x, right, is in the direction, which direction? Right. And electric field at A due to this D,
Be right.
again this is the right. And if two electric fields are there in the same direction, we can add them. And if they are, since they are vectors but they are in the same direction, right, so we can just simply add the two electric fields. So but how we'll do, first we should find this, no? So what would be EAX? Will there be any electric field other than due to x and d at this point? No, because there are only two charges, right? So we have covered on both of them, this charge as well as this charge. Now find EAX. So it will be K, right? And then Q, which is plus 10 to the power minus 8, isn't it? Ignore the positive sign because KQ by R square. What is R? 2.05 square, correct? And we will also have to indicate the direction. So let's indicate this by, can we write AD unit vector, isn't it?
Yeah.
From A to D, this unit vector. Now next is
Uh,
EAD, right? EAD would be
yes.
what? Q, again the same Q, divided by R square, and the direction would be the same this time around also. So the net electric field at a, let's say this is E1, okay? So this would be the addition of both of these electric fields, EAD and EAX, right? It's simple, you can just add them. So I can see that this answer was coming around to be 3.6 into 10 to the power 4 Newton per coulomb,
Coulomb.
and this is also the same 3.6 into 10 to the power 4 Newton per coulomb, correct? And with AD vector, this AD unit vector. So if you add them, what you will get? 7.2 10 to the power 4 AD unit vector, right? Or you can, if you,
Wait,
what?
1.9 Newton per coulomb.
Yeah, this is Newton per coulomb. This is the unit vector AD. Okay. So have you got the first part?
Yes.
Now let us move on to the second part. Second part is we want to find the electric field at point B. Where is this B? This is the point B, right? So let us first erase this because the figure is upwards. Can I erase? Should first erase this thing. I select and erase. Yeah, I can do that way also. Okay, so for second part, we want to find electric field at B. Sorry, not A, B rather. Correct? I will do. You tell me this time. We mentioned this thing. Just a second. Okay, So at B, due to C, no, there is no charge.
X.
Due to X, it would be in this direction. And due to this D, what would happen? It would be in the direction opposite, right? So in this case, we would write, let's say, E at B due to X, right? It would be what? K Q divided by R square. What is R? 0.05, correct? And it is in the direction, you can say, CB unit vector. Okay, so this is done. Now for the next electric field at B due to this D, it would be K Q on R square. So R in this case would be this plus this plus this. So 1 plus 0.05 it would be, isn't it? So it would be 1.05. So let's write it 1.05 square, and this direction is, you can say, AD vector or any vector, BC vector. Okay. Yeah, this is in this direction, BC unit vector.
That's X.
Oh, sorry, X.
Also for the above one.
So XB, right? Let us draw it again. Okay, anyway. So what would be the net electric field? Let's say it is E2, right? So what would be that?
Uh,
See, in this case, we cannot add them, right? Yeah, we would subtract. So, first thing first, what is this magnitude? Let us write the magnitude. It is the same,
just the difference.
and it's in the direction XP vector. But this one would be different because it is 1.05, right? So it is 4 into 10 to the power 3 Newton per Coulomb. Bx unit vector. Now which one of them is greater in magnitude? This Bx one, right? Because this is 10 to the power 4, this is 10 to the power 3. So now what we can do is we can write E2 is equal to EBX minus EBD, and it would be in the direction which is bigger one.
So X.
Do you remember this? We studied this in vectors. Now if you solve it, what you would get? You would get 3.2 into 10 to the power 4. Okay,
X.
Newton per Coulomb, correct?
Yeah.
This is done. Now we have another part, third part.
Which is C.
Yeah, for C, what we have to do? Should I erase this first?
Yeah.
Let us erase this.
So C will experience, what do you call that? Electric field.
Now you will have to deal with vectors in this case. You know?
Okay, yeah, the fire to the ground.
Yeah. See, he has already drawn it for you. So first of all, what we'll have to do is, he has given the length. So from X to C, this is 0.1 meters, and from D to C, it is also 0.1 meters, and this was also 0.1 meter. That means that it is an equilateral triangle.
Yeah.
Now at C, there would be two electric fields, one due to this charge at X
C and D.
and one due to this
X
D.
and
So he has marked the electric field at C due to X as even, and it would be in the direction going away from it, right?
Yeah. C equal.
But for this charge, D, it is negative, so it would attract this, and therefore the force would be like this. Okay,
Yeah.
so at you can draw this. This is even, or and this is the another force due to the charge at D.
C. Yeah. So E2.
E1, E2. Oh, sorry, this E2. And what we have to do, we have to find the resultant of it.
So it would be the.
How can it would be in the middle?
I
It
mean,
depends, you know, it
yeah.
depends. First of all, you want to find E1. What would be E1? K Q upon R square, which would be 0.1 square, isn't it? Are you there? Hello? Hello? Where have you gone? Okay, so we'll find this E1 and E2, magnitude of E1 and E2. So what would be the magnitude? So KQ by R square, right?
Yeah.
So this would amount to how much? I think it would amount to 9 into 10 to the power 3, okay? 9 into 10 to the power 3 Newton per Coulomb. And same thing for E2, because the distance is the same. This distance is same, and the charge magnitude is also same. So again, KQ by R square. Are you there?
So.
It will also be the same.
Okay.
So 9 into 10 to the power 3 Newton per Coulomb. Correct? Now what you need to do, since see here, this E1 magnitude is same as E2, right?
Yeah.
Now we want to find the resultant. How do you find the resultant of two vectors? Using parallelogram law.
Yeah.
And for that you need to find the angle between two vectors, which is theta.
Yeah.
So what is the angle between these two vectors?
120 degrees.
How much?
120.
Yeah, obviously, because this whole line is 180, right?
Yeah.
And then since this is 60 because of equilateral triangle, so this angle would be 120 degrees.
Yeah.
So this is 120 degrees. And we know one thing, you know what? When there are two vectors of equal magnitude, so E1 magnitude is equal to E2 magnitude. I told you is this in vectors, and the theta, the angle between them is 120 degrees. Okay,
Yeah.
so this is something that we should remember. The resultant would be midway because they are equal in magnitude, right?
Yeah.
So this should be in this direction. Let's say this as ER resultant,
Yeah.
and it would be, okay,
Yeah.
so it would be 60 degree, 60 this and 60 this. Now you can say that this direction of ER would be parallel to the line, this one. Okay,
Yeah.
why? Because they make alternate interior angles. This is 60, this is also 60. So they are making alternate interior. That is why this line should be parallel to this. All right.
Okay.
So we now know the direction. Now can you find the resultant? So ER magnitude would be equal to how much?
Sorry.
Under root
Under root E1 square
plus
plus
E2
E2
square.
square plus 2 E1 E2 cos theta.
So if you go on to find this, now since here E1 is equal to E2, right?
Yeah. So
So
we
you can
can,
write E1 square, 2E1 square
yeah. And
plus
then
2E1 square again, I think.
yeah, 2E1 square and then into minus 1 by 2.
Cos 120 is how much?
Minus 1 by 2.
So under root 2E1 square 1 plus cos theta, that means 1 cos 20 is minus half.
Yeah.
So we have done that. Now this would become half into 2, which would get cancelled, and E1 square, which is just E1, isn't it?
Yeah.
So ER magnitude is equal to the magnitude of E1, right?
Yeah.
That means the resultant would be the same as either of the two. Okay.
Yeah. Yeah.
So ER magnitude would be what much? 9 into 10 to the power 3.
Power 3 Newton per coulomb.
And the direction, because since this is the magnitude, we should specify the direction separately. So direction would be parallel to this line CD. Okay, no, not CD, AD
8
or XD, whatever you say.
XT. Yeah.
This is the final answer.
Yeah.
Correct?
Yep.
So you should remember this. What? When there are two vectors of equal magnitude inclined at 120 degree, the resultant is equal to the either one of them.
Okay.
This is your point you should remember, because but in the boards you should not write directly. I am talking about the competitive examinations. In the board you should solve it, right? You cannot write it directly.
Okay.
So this is the way you should solve the board. So this question is done. I think it is enough for physics today.
Okay.
Okay.